Hi, in this video, we're going to take a look at unsupervised learning. Specifically, we're going to look at clustering. All right, clustering, my goal is to get my data into subgroups where each group has like similar data points. All right, so what we want to do is I'm going to run this algorithm. The algorithm is going to go through and it's going to group the data in some way, some shape, some form mathematically, and it's going to say, and it's going to try and in some optimization method determine which are the best subgroups, what are the best groupings if I want each group to be as similar as possible. All right, so why do we do this? All right, so when we do clustering our data, it can either be for segmentation, outlier detection, feature engineering, or subpopulation detection. Those are the major reasons. Also inference, but inference can be difficult at times. I guess I should include inference. Go ahead and just put that there. All right, for segmentation, what I want to do, I want to break up my data in a manner, I'm going to break up my data into different groups, and I'm going to use each group differently. So imagine I have a bunch of clients, and I've got 5 team members to support my clients. What I could do, I could take information about the clients, group them into similar groups, to 5 different groups, and then hand each team member a different collection. That can be their caseload. All right, now why would I want to do this? Well, if I do something like this, then each team member is working on a similar group of clients over and over and over. So they can be like a specialist in handling particular issues for the customers. So they get better at handling the issues that each customer individually needs. It'll just be more reflex to them. And we do this all the time, but usually we do it by geography or some other feature. So maybe like type of client, or maybe, geography is usually the big one. Now, but you might want to consider letting the data speak for this. Now, the next reason that we would want to do this is for outlier and anomaly detection. So an outlier, is like one value in the data is kind of like different than the rest. Anomaly means that, the group, like an entire rows collectively as a gestalt is off from the rest of the data. All right, so I'm grouping my data into similar data point groups. All right, now what would be the impact of having a group with just one observation? If I have a group of 1 in there and I'm grouping data by similar data values, then that 1 point is not similar to any other data point. That sounds like an anomaly or an outlier to me. So in that situation, I want to go, hey, I want to double check that data point. I want to check that one row of data. I want to double check that, is it correct? Does it belong in the data? Was a mistake made? Was it, is it intended to be, different population altogether? I don't know. Well, the goal is to find the things to investigate off of that. Next one is for feature engineering. All right, so, and this is where I use clustering the most personally in my work. In this situation, what I'm going to do, I'm going to group my data points, and then I'm going to use like the label of each group as a categorical predictor variable, a nominal predictor variable. Something that's important about this is that when I do this, the groups are categories. If it's group 1, group 2, group 3, group 4, that doesn't tell me which one's greater or less or anything like that. It's just group 1, group 2, group 3, group 4. That's all it tells me. So the label is categorical. It's not ordinal. It's not interval, and it's not ratio data. Now, one thing I like to do, I like to use binary. So I'll just have 2 levels and I'll convert it to 0s and 1s. In that case, it's okay to treat it as numbers because it's 0 and 1. It's just a dummy variable situation, and that's all right. And that's the way I prefer to do it. Next thing I want to do is for subpopulation detection. This happened to me one time where I get some data from my client. Now, my client wants me to do, some modeling, wants me to do some statistics. Great. I'm working through and I'm like, wow, there's something wrong with this. Something's weird with this data. Something's going on. And as I'm working through, the thing just never really sat right with me as I kept on working through. I was just like, oh, that's funny. Oh, that's funny. Well, what ended up happening was that the data was from a company that resulted from merging two companies together. And part of the data was from company A, part of the data was from company B, but the people who were handling the data just thought, hey, let's just throw it all into one pot. And they didn't label where did the data come from. All right, so as I was working through, it's like my models weren't working out. Like, I was checking model quality. Like, I was like, I knew this was not going to be good. And this, there was a problem. How did I address this? Well, what I ended up doing was I ran clustering. I was able to figure out pretty well where each data point came from. And then if it was company A or company B, and then I separated the data, I built my models, and everything worked out great. Now, next one is inference. If we believe that there's like subpopulations and we want to figure out what are those populations and what are the features like that are related to those populations, breaking it up can be useful. All right, now this next part, this is the most important part of this video. If you get nothing else from this video, get this one part. Clustering is not a supervised learning method. Clustering is not a predictive analytics method. Clustering supports supervised learning. Clustering supports predictive analytics. Now, we can use clustering to break up our data for supervised learning, and we use clustering to get a new predictor variable, but it is not a predictor method by itself. The algorithm only works with the predictor variables. It doesn't touch the target variables. Well, if it doesn't touch the target variables, it does not tune to the target variables. If it does not tune to the target variables, we could do better. All right, so if you could do better, and it's easy to do so, just do better. It's not, it's not hard. For some reason, I consistently run into people getting this mixed up, including like PhD students. I don't know what's up. If you feel like clustering is going to be a good way to go for predictions, then you can use k-nearest neighbors or proximal centroids for your prediction method. And then you're using a supervised learning method that tunes to your target variable. K-nearest neighbor has some nice features to it. I find that proximal centroid is good because it's so easy to explain. It's simple. When you get into your data mining 1 class, you'll go over that. It's not complicated. It's pretty simple, but I use it a lot at work because I can explain the model to people who do not have math backgrounds. Think about like regression. Regression, you have to have at least, college algebra math involved. People don't really gravitate towards that. Proximal centroid is even simpler. Now, our methods for clustering. There are tons and tons of different ways that you can go on the net and you can find a bunch of different like journals on different algorithms, and you could spend the rest of your life looking at the different ways to do it in R. But there are 3 major classes of clustering that we use. There are other ones. If you look at the scikit-learn webpage, they've got a bunch that don't fit these 3 categories. That's okay. These are the major ones that you're going to encounter the most. So those 3 categories are partition, hierarchical, model-based. All right, partition clustering is basically I take my data points and I just put them into different groups by some mathematical algorithm. The most commonly used one of that is k-means. Now, k-means, I'm using a mean, so immediately that's sensitive to outliers in my data. So just be aware of that when you start using it. Hierarchical clustering, either agglomerative or divisive. What this does, this either puts all the data into one group, breaks it up into smaller groups, break it up into smaller groups, break it up into smaller groups, keep on breaking up the groups until each data point is in its own individual cluster. That's divisive. Agglomerative is each data point starts in its own group, and groups get combined. Oh, and then you combine groups until you have just one big group. All right, so hierarchical is whenever you see like a dendrogram, then that is a hierarchical clustering method. Next one is model-based clustering. In this situation, I believe that my data is coming from different theoretical distributions. So usually it's a Gaussian distribution for this, or maybe or possibly T distribution. I've seen that too. So I believe my data is coming. I've got my data. I believe that there might be 3, 4, 5 subpopulations of Gaussian variables. What I want to do, I want to identify what are those Gaussian distributions. And I find that usually this is better theoretically than it is operationally. I've never used it at work, honestly. I've never seen an advantage over k-means or the other techniques for partitioning. I use hierarchical clustering probably the most, and then k-means after that. All right, so now let's go ahead and take a look at an example in R. We're going to use the iris dataset. This is a classic dataset. So let's go ahead and generate a pairs plot. So here are the numeric variables of length, width, and here so we've got the plots, and I've got them colored by the species. So we can see that there are 3 different species, black, red, and green. And if we go like this, Setosa is the black, Versicolor is the red, and Virginica is the green. I hope I said those words correctly. If I did not, make a comment in the comment section. I don't know, do something. All right. Whenever I do partition clustering or hierarchical clustering, I strongly want to consider normalizing my data, or possibly setting it up so it goes from 0 to 1, -1 to 1. I feel that normalizing your data is a better choice because it's less sensitive to extreme values, but do whatever works for you. All right, so what we're going to do in R, to normalize my data, I'm going to use the scale function. And I'm only working with the numeric variables. When I drop this in, I'm not worrying about the species. So there's M. All right, so let's take a look. All right, so e to the -16 is super close to 0. E to the -17 is super close to 0. So up to machine accuracy, after I've sent it through scale, the average is going to be equal to 0, and we can see that the standard deviation is equal to 1 for each column. Now, if I'm doing model-based clustering, I don't want to do this because it'll mess up the relationship between the different dimensions. All right, when I do k-means clustering, I need to build up I need to either have the computer randomly pick centers, or I need to pick them. If it randomly picks centers, it's going to randomly pick data points. I always specify what it is, and I do that so that way it's reproducible down the road. I'll get the same result regardless of like which machine I'm going to use, which computer, which version of R or Python, whatever. So I always specify it. So here in my first group, I'm setting it up so that initially I'm going to say, hey, this first point I'm interested in has 3333 for all the values. The other one has -3 for all the values. What k-means clustering is going to do, it's going to take a data point. It's going to look, is it closer to the first center or is it closer to the second center? So at this point, it's 3 and -3 for them. Now, why am I picking 3 and -3? Remember, I normalized, right? since I normalize, 3 is, pretty extreme on standard normal, and -3 is pretty extreme for standard normal. So I'm kind of spreading it out. I'm forcing my centers to be apart from each other. All right, now as I go through k-means algorithm, it's going to go through for each individual observation, each row of data. It's going to go, hey, is this closer to the first one or the second one? Is it closer to the first one, the second one? It goes to the next observation, first one or second one, and it goes through and it picks which one's the closest. All right, so now I've got groups. What it's going to do, it's going to take the average of each of those groups. Those are my new centers. So these values will get replaced after my first round of grouping. And then it's going to repeat the algorithm again. Then it's going to make new values for the centers, and it's going to repeat this process again. It's going to keep on doing it over and over and over until it looks like things aren't moving around, or we tell it, hey, after so many, just stop. K-means is very fast. It takes very few iterations. This is a good algorithm to work with for big data. All right, so let's go ahead and let's see. All right, so I'm running the k-means algorithm, and I'm using the centers that I just defined up here as the center each time. Let's look at what happens. All right, so when it's all done for the new center, and remember, this is my rescaled data, I've got 1/2, -1/2, -0.7, -0.6 is the new first center, mostly positive values. For the second, I've got -1, 0.9, -1.3, and -1.3 for the second. And you can see on the second one, I've got mostly negative values. Now here, I can see that just by happenstance, the first rows are the ones that are going in group 2. That's the one with the negative values initially. And then I can see that the later rows are going into the first group. That's the one that started out with all those 3s. Now this gives me an idea of how good of a clustering I have. And this lists out all of the components of the clustering object that I just built, k-means_iris. All of these aspects are inside k-means_iris, and I can take a look and grab them and use them as I see fit in my programming. All right, so do I have good clustering? That is a question that is ultimately a subjective answer. Is this good enough to work with? Well, the first way that I always work this out is I do a principal component analysis plot. Okay, principal component analysis. What is this doing? It's PR comp in R. This is going through, and this is looking at the data, and this is saying, hey, could I change the data? Could I rotate and reflect and translate over the data points in a manner so that the distance between points stays the same, but I have my axes are more parallel to how the data looks in higher dimensional space. For us, we really don't have to worry about it. When I say rank 2, this is basically the best 2-dimensional approximation of the data that we could get under Euclidean distance. Don't really need to know that for this class because I'm not going to test you on it. You're done. You've got your last homework assignment. All right, so here I went ahead and I created 2 new coordinate systems based off the data, where PC1 goes along like the largest, like higher dimensional line segment that pass through the data cloud, and the second is perpendicular to the first. And we can see that in this format, there are 2 distinct groups. Is that consistent with what we looked at earlier? Well, I know from looking at the pairs plot that this is probably one of the particular points, or one of the species, and the other 2 are grouped up over here. Now, you'll notice I've got these colored by the k-means cluster. You can see I've got black and I've got red. Do you see that there's a pretty good separation between the red cloud and the black cloud? I have a good separation between the red cloud and the black cloud. So that makes me feel confident that I have good clustering. Now let's take a look at what happens if I do the same plot, but I color by the species. Well, here we go. So we can see that the first species is over in this cloud by itself, and then these two are, floating around this cloud, and you can kind of see that there's more green on this end than on this end. Now let's do a pairs plot, but this time we're going to color by the clustering group. So remember, I've got 4-dimensional data, and I'm representing just 2 at a time at each of these subplots. So the principal component analysis takes the 4 dimensions, and in our case, we drop it down to 2 dimensions. We're trying to get the best 2-dimensional representation of 4-dimensional data. And we can see that we got pretty good separation, good separation, good separation, good separation, good separation, and good separation. This is a good clustering. Now we know that 2 of the species are getting grouped together with this clustering. So with that prior, if I had that prior knowledge, I would consider maybe going with 3 different clusters, and I can use these plots to guide to me on how many I should have. All right, that's all I've got for you. I hope you're staying healthy. Take care and goodbye.